Okay, so it's my great pleasure to introduce Stephen Maldonado. Excuse me, I always mispronounce your last name. Maldonado, is that close?
It's close enough. It'll work for now.
Oh, I'm sorry. And he's going to be speaking with us today about deciphering voltammetry with semiconductor electrodes, which is a topic that I enthusiastically really appreciate. And so just for everyone's awareness, so Stephen is a member of our scientific advisory board for our center and is also a PI in the Department of Energy, Basic Energy Sciences Solar Photochem program. And Alyssa and I had, and among others, had the opportunity to see him speak at the annual Solar Photochem meeting in May. And so we thought he would be a great speaker for specs to give us the conventional semiconductor perspective for charge transfer mechanisms. So with that, Stephen, please take it away.
Okay, great. Thanks, Erin. Let me get my screen set up. I can't always tell with multiple monitors. Are you able to see the full slide or just the presenter view, or I guess what version of PowerPoint are you seeing?
We cannot see presentation mode. We can see your slide with your, like, on the left side, all of the slide deck. And now we're in presenter view. Yeah, I think if you go to display settings and switch mode at the top there.
I've gotten rusty at this. It's been a while since I've done a Zoom one. Okay, how about now? Which version of PowerPoint are you seeing?
Still just the version where you build it. And now presenter view.
How about that?
Perfect.
We got it? Okay.
You're good.
All right, awesome. Thank you. Okay, I'm going to give a talk about semiconductor electrochemistry, trying to understand voltammetry data, actually. And this is largely based on a talk I gave earlier in the spring that Erin and I think Gary, who's here on the call, heard a version of. And so some of that might sound familiar to you guys, but hopefully for the rest of you, it kind of gives some insight in terms of how one makes sense of what I would call kind of kooky looking electrochemical data. And I'm really interested in charge transfer processes between molecules and inorganic, let's say, hard semiconductor electrodes. So I'll just give a couple of brief bits on background. For those of you who are less, I guess, in tune in terms of traditional hard inorganic semiconductor electrochemistry, just the bare bits in terms of why this might matter. There's a lot of interesting architectures for molecular memory, and this has been going on for a couple of decades in terms of charge transfer between things like silicon and redox active molecules and molecular assemblies. A technology that I've been interested in since I was a grad student are dye-sensitized solar cells, where clearly you have redox active molecules interacting with semiconductors like TiO2. And then you have the activities in the current solar fuels hubs that are largely, or if not entirely, built on the premise of charge transfer between inorganic semiconductors like silicon, gallium arsenide, et cetera, and molecules that do catalysis or chemical conversion reactions. Okay, so I'm not going to talk about any of these applications per se, but everything that I will talk about is with the premise of collecting data that serves the purpose of one of these end goals. And if you have a particular end goal, then this is for you. Perhaps a more essential primer in terms of what I'm going to talk about is the idea that when you get electrochemical data, what you should start to think about or ask yourself first and foremost to interpret what you're seeing is, where is the potential being distributed when you apply a potential to your electrode or to your electrochemical cell? And to this, I would point you to this excellent work by Henry White that came out about the time I think I was in 6th grade, maybe 7th grade. But to me, it's one of the best electrochemistry papers and really relevant for the purposes of most of the data I will talk about today. And his whole premise, which was actually built on ideas that predated him by several decades, was that the data that you acquire, in this case for molecules stuck on an electrode, so if I can turn my laser pointer on, so this plot on the right is a normalized version of current versus potential data, a voltammogram. And the data that you get, the shape of it, all of it has meaning. And it relates to where charge gets distributed when you try to push electrons in or out of the system. And this is a little bit different than what is, I would say, the dominant description, at least in the major textbooks that you come across. But it's this idea that electrostatics is not only a part of electrochemical data, but it's an essential insight in order for you to get meaning out of what you're trying to measure. And this paper advocates this in great detail. Okay, the last background, which may be either the most essential or non-essential bit about this talk, is this concept of an autostereogram. So that's a fancy word for what was called magic eye images. And this is something that may be familiar to you if you're like me, a child of the 90s. Autostereograms are these pictures that you see on the screen. They're these sort of benign, maybe pleasant looking repeating images that you used to be able to find in malls all across America, where the idea was you look at this image and you see colors and patterns. But if you figured out how to look at this image differently, there actually was information encoded and embedded in this. And I think maybe Gary gets my point here, that these things were both super popular, but super annoying, because if you stared at this in the conventional way, you didn't see anything. But if you learned how to cross your eyes or maybe look at this sideways, you could see something else pointing out at you. And what I'm telling you right now here on this slide is I have encoded in these images a message to you that is borderline maybe inappropriate for this talk. But until you know how to look at this, that information or that message is lost. Okay?
Do I tell them what it says, Stephen?
I'll get back to you at the end, Gary. I'll get back to you at the end.
Okay.
Okay, so that's the context for today's sort of talk about what I'll describe. Okay, if you get those three things, then you get enough to get the gist of what I'm going to tell you. All right. The type of experiments of the data that I'm interested in understanding are voltammetry plots collected with semiconductor electrodes. So here is a plot taken from an old Al Bard paper contrasting electrochemistry for a redox active molecule that may be one of the most historically well-studied, rubipi, using either a canonical metal electrode, a platinum electrode, and that's the data on the bottom, or a semiconductor electrode, and this would be an N-type silicon electrode, the data on the top. Okay, the point being is that the data between these two things look somewhat similar, but they are clearly not identical. And I should make a minor point aside. All the data that I'm going to show you, I think without exception, follows the Texas convention in terms of positive potentials, meaning a reductive current, negative currents, meaning anodic. That's just the way I like plotting things. I don't like the UPAC convention, but if you do turn your screen, around 180 degrees, all the data should make sense to you. Okay, the problem with these data that you can get with a semiconductor electrode is that they're ridiculously easy to obtain. But interpreting that data relative to the metal electrode is incredibly complex. For a metal electrode, there have been books and thousands of papers written on how to interpret and understand all the nuances and the details of charge transfer between rubidium and platinum, a molecule and a metal electrode. For a semiconductor electrode, if you look at the literature, if you look at all of sort of the most advanced treatises on electrochemistry, there's really nothing. The general gist of it is that it's complicated, that it looks kind of like the metal electrode case, but there's otherwise no way to interpret in a meaningful level what that data says. So I'm going to tell you in this talk the parts or the ways that you actually bridge that gap, sort of fill out what has been missing in the electrochemical literature for the last several decades. Okay? And I will emphasize that this is not meaning that we're going to try to figure out how to take a solid state diode, the physics answer to a semiconductor device, and sort of jam it into a chemistry context, which is what's usually done. Instead, what I'm going to try to tell you is this is the format that we believe is the way you should be thinking about semiconductor electrochemistry data, and it doesn't rely on you understanding anything other than what I'm going to tell you now. The first part, which I believe is at least a part of several of your guys' works, and that is this Marcus Gerischer framework in terms for understanding the contact between a semiconductor electrode and a solution. And the plot here on the left is an image of this contact between, in this case, an N-type semiconductor, where you can see the sort of identifiable band structure, the valence and conduction bands, and the Fermi level is denoted by a dashed line for those of you that care about that sort of thing. The right side on this picture is a picture of the solution, but drawing the solution to be sort of a fake amorphous solid. And this was sort of the trick that Gerischer brought to this table. In order to describe things between a semiconductor and a solution, the easiest way, at least to start, was to make the solution look like a solid in the sense that it also had a conduction and valence band. But in this case, the conduction and valence band of this solution slash amorphous solid would be the population of redox molecules A, so molecules that could accept an electron, and redox molecules A minus, those were molecules that had already accepted an electron. Okay. And the idea then with this picture is if you draw this in such a way, then the overlap between these two bands here represents where charge transfer, electron transfer from this N-type semiconductor can move from the semiconductor into the molecule, into these molecules A. And this horizontal bar here in yellow, that represents the overlap at the conduction band edge, the bottom of the conduction band of the N-type semiconductor at the interface. And so it's literally the overlap in that horizontal slice that dictates the charge transfer rate constant. And that's what's shown over here. And for those of you who like a more molecular description, this is sort of the classic Marcus description of a charge transfer rate constant between donor acceptor molecules. It's the same thing. Okay. And so you can predict what the value of this charge transfer rate constant, KET here, from reorganization energy, from the driving force between the redox potential of the molecule and the band edge position. These are all identifiable things. The important point here is this has nothing to do with the diode equation. And so if you're waiting for something like a Richardson constant to show up or whatever, throw that to the side. You don't need it. What you do need to understand is that the overall forward and back rate constants for charge transfer, electron transfer for this system, the forward and the back rate constants, are a product of this intrinsic Marcus type rate constant multiplied by the availabilities of charge carriers at this surface. And so this N subscript S, that's the number of electrons that are at the surface. The reverse rate constant is related to this KET again, and the number of electrons at the surface when the Fermi level is exactly equal to E0. So that's sort of our reference state. Okay. Okay, where does this matter? How does this affect things, or how does this make things understandable? Well, at first, it doesn't make things understandable. In fact, when you start to wrap your head around this, you start to realize this is even more complicated than you might consider at first. Okay, here is a picture of two identical contacts, and we're going to do a quick simulation. On the left, we're going to simulate what happens when you apply a negative potential. And so I'm going to move this Fermi level up higher on the vertical axis. And we're going to apply a negative potential, and we're going to see how this system should be behaving, how this electrode and the solution with these redox molecules, how they will interact with each other. In this picture on the left, as I apply a potential, and I move the Fermi level more negative, I move it up. What I should be doing principally is make this barrier for electrons deep in the semiconductor smaller in order for them to reach the interface. And thereby, when I do that, I make the electrons more plentiful at the interface, and so I can react more of those electrons with more A molecules to make A minus. And the important point to consider here is when I apply a potential, this is the only thing that's changing, that amount of band bending in the semiconductor. And again, I apologize for many of you if this is sort of a no-brainer concept. This, though, you should realize is the ideal case. When I'm applying a potential, all the action is really just changing in the semiconductor. When I look at the picture on the right, we're going to do the same experiment, except now when I apply a potential, you'll see that not only is the Fermi level moving, but everything is also starting to shift relative to each other. And when that happens, what that means is that the potential that I'm applying, some fraction of that is not being dropped in the semiconductor. Some fraction of that is being dropped elsewhere in the system. And what does that mean? Here in these two cases that I have now on the screen, even though I've applied the exact same potential, the Fermi level, the dashed lines here at the exact same vertical position. In this experiment, even if I had the same semiconductor and the same molecules in solution, the rate constant that I would measure or that I would interpret would be very different, because you can see this overlap now between the band edge and this population of molecules here in this right case is different than what it is in the left case. And so this complicates things. This makes now it important for me to understand when I make a measurement, does my system look like what the picture on the left looks like, which is the ideal case, or is the picture on the right now possible, where potential is being lost, not where I want it to be, but also in other places? And is that affecting my ability to understand the true innate chemistry? Okay, the second part of this answer in terms of knowing where the potential applies means you have to look at this same interface between the semiconductor and the electrolyte in a little bit more detail. So rather than plotting an electrochemical potential on the left scale, we're going to think electrostatically what happens when I apply a potential. So this right bar here represents the magnitude of the potential that I'm telling my potentiostat to apply to my electrode. And so this ideally is the amount with respect to a reference point that I should be moving the Fermi level of my semiconductor electrode. However, in a real system, only a fraction of that will actually change the Fermi level of my semiconductor, this blue bar. The remaining fraction of what I apply will be dropped across the interface if there is anything at the interface, and we'll get to the details of that in a minute. And it will also be dropped in solution, in the electrolyte. That's unavoidable. That's a physical fact that this happens. The ambiguity comes into play in terms of how big are these relative blue, green, and brown bars. Effectively, for the moment, we can think of these blue, green, and brown bars as fractions, fractional values. Each one of these describes a fraction of the total potential that I'm applying. And some fraction of that is dropping in the semiconductor, some fraction is dropping in the surface, and some fraction is dropping in the electrolyte. If you're a little bit more mathematically inclined, you can think of these fractions as describing the derivative of where the electrostatic potential drop is changing in each of these regions with respect to the potential that you're applying. If you don't like mathematical descriptions, then forget this equation and just focus on this bottom one, which says that every time you apply a potential to any system, the fractional potential drops, which I'll label as gamma values, all have to equal 1. That's by definition. This is still the second part.
I had a question on this. Could we just go back one?
Yeah, sure.
So in the math, we're not supposed to pay attention to, you have 3 little d's. Correct? 1 is equal to little d times 2 phi something minus phi something else.
Yeah.
What are those? Why are those all the same? I thought one would have been a W and the other one would be, I don't know, some double layer thing.
These are derivatives. So I'm sorry, this is the
Oh,
derivative.
shit. Okay, you have D in 2 places and they mean different things. Okay, sorry, that's obvious.
Yeah, I'm sorry, apologize for the notation, but yeah, what I meant to say is that these are all derivatives, technically partial derivatives of how the electrostatic potential change here is changing with respect to the applied potential.
Okay, in that case, okay, these are all derivatives. Never mind. Okay, so you're looking at differentials. Got it.
Okay. So the question then is what is the value of these fractional values, or if you want to be more pointed, of these partial derivatives? And if you do Gauss's law analysis of any electrochemical system, you will come to the same conclusion. And that conclusion is that these fractional values, or the derivatives with respect to the electrostatic potential drop and the applied potential you're giving to the system, is related to the capacitances of each of these regions, each of these components of your semiconductor electrolyte interface system. Okay. So in the case where we have a semiconductor in contact with a solution that has a Helmholtz layer and a diffuse layer, if you want to get a little bit more detailed in terms of the structure of the electrolyte, and maybe there is an oxide developing at the interface, which is usually the case on an inorganic semiconductor, the fractional potential drops then can be described as these 4 gamma terms, which are functions then of the capacitance values of each of these regions. And the key point here in all of this is that for any given system that has specific capacitance values, or permittivity, effectively is what really matters here, is that there's only one real set of gamma values that will describe your system for any one condition. And if you know what those values are, then you can go back and start to make sense of what the electrochemistry ought to look at, or ought to look like, I should say. So that's the third part of the answer then you have to get to, is that if you know what these fractional values are, how do you go back and use that information to tell you what goes on in this system that I described before, which is basically where all heck is breaking loose, and when you're applying potential, it's dropping all over the place. This is really, I would say, the first example here in this entire presentation thus far where we've added some value. And what we've done in terms of this whole discussion and our contribution to this answer is we've written these rate constants for the forward and back processes of electron transfer explicitly in terms of these fractional values. And that, believe it or not, hadn't been done before in this field. But with that in mind, if you have these fractional values, then this mathematically, what I've highlighted here in these yellow boxes, is the way that you account for physical systems that look like what I'm showing you on the slide, where the potential is dropping in these different regions and how that is affecting the rate of the reaction and, in your perspective, the current that you measure. Okay, the fourth part of the answer in terms of making sense of all this is in any electrochemical experiment, there's always going to be some interplay between reaction kinetics and just mass transport of the species that you're trying to reduce or oxidize. And ideally, you'd like to eliminate any sort of temporal dependence on mass transport because that complicates things. Not necessary, but it makes things much easier. Okay, so now we'll get to actually the starting point of my talk. And I'm sorry for that was a really long-winded setup, but it's really the way you get through the rest of this. I'm probably not going to have time to talk about these three different, what I would call magic eye images of electrochemistry of semiconductors. But these data that you're seeing on the screen here are all interpretable in terms of information between the interaction of a semiconductor and a redox molecule or sets of redox molecules. But using those sort of 4 parts of the answer, we can figure out exactly what these things mean. Because without that, if you're like us or my students, when we first collected each of these data sets, now roughly 1.5 years, 2 years ago, we had no idea what they meant. But it turns out if we know how to look at them, they have a lot of really good information in terms of each of these systems. So I'm going to start then with a system where we can easily check off that 4th part of the answer. We're going to look at systems where there's no mass transport whatsoever. And that means we're going to stick a redox molecules directly onto the semiconductor electrode surface, in this case, silicon electrodes. And the principal reason for doing that is it just makes the math easier. We don't have to worry about the fusion or anything else. Okay. Again, the context of this, I'm also interested in dye-sensitized solar cells. So there is some natural analog to that, but I'm not going to talk about any application. We're just going to think about experiments where we take measurements with molecules stuck on semiconductor electrode surface. If you care about the details, all the data that I will show you or mention in today's talk are stuck on silicon in the following way, was shown on the screen. Essentially, we're big advocates of using Grignard chemistry on activated silicon surfaces to stick redox molecules of interest to. The 2 pathways that I show you on top and bottom are essentially identical. The only difference is that when you stick a rather large molecule on a silicon surface, just due to steric crowding, you cannot literally hit every atop atom. And so that unbounded or unreacted surfaces will at least start out as being hydrogen terminated. But if you're working in air or anything that's not ultra high vacuum, that hydrogen terminated silicon site will eventually oxidize and become a defect site. And so because of that, we tend to favor this backfilled approach where we fill in all these holes with small methyl groups, which can kind of fit in and still passivate and protect the surface while allowing us to have a secondary functionality. And for all of the talk today, I'm just going to talk about sticking on viologen redox groups. And the viologens will basically just differ by the terminal R group sticking away from the surface. I guess for the sake of time, I'm going to skip some of the details here. I'll just say we took great pains in terms of preparing molecules attached to silicon where we know that the defect tensity as measured by photoconductivity measurements is pretty low, or about as low as you can get. And I will probably only today focus on data where we have defect densities on the order of about 10 parts per million, which is about as low as I believe anyone could reliably get on a chemically modified semiconductor surface. The point being is I'm going to try to make the argument that all the weirdness that I'll show you in the data has nothing to do with surface states or some magical, black, undefined, dark, mysterious reason. Right? It has nothing to do with recombination that hasn't been described. Instead, is a direct result of how electrochemistry works on a semiconductor. Okay, so here are the types of data that I'm talking about. Here's an N-type silicon electrode. We're studying this in methanol. We're not shining any light on it, and we're using an inert electrolyte in the background, but we've stuck onto it a viologen onto a surface that has nominally not enough defects for them to matter. And we acquire data that looks like this as a function of scan rate. So these are all voltammetry plots just at different scan rates as indicated in each of these panels. Now, the interesting thing with these data right off the bat is you see that the data, the shapes, particularly of that first redox wave, is highly dependent on the scan rate. The second redox wave is not really dependent on the scan rate beyond just the amount of IR distortion that happens when you start passing a lot of current at large scan rates. But the redox event here on the right side in each of these plots kind of looks like what a molecule gives on a metal electrode if you stick it on its surface. But this first redox wave, that doesn't. And It turns out for viologens and silicon, these first and second redox transitions sort of straddle the band edge. So this first redox transition occurs in the band gap region of the silicon. So the semiconductor is nominally in depletion. In the second redox transition, silicon is in accumulation. So it has more of a metallic behavior. I'm going to focus on, for this talk, the reason why the voltammetry for this viologen, the first redox transition in depletion mode, why this return wave disappears, why there's an asymmetry. And that's what's kind of interesting. Okay, coming back a little bit, I forgot who brought this up, but here's another example where we have to pay a little bit more attention to the math. And again, these D's here that I have on this slide and the next couple slides are all representing a derivative. If you want to think about what happens in an experiment where you have redox molecules stuck on an electrode that start off in one oxidation state and then convert into a different oxidation state, you can formulate that as a math problem, basically. The current density that you'd measure is related to ultimately the change in the fraction of molecules that are in this case, the A form, as a function of the applied potential. So this top way of writing this is how I might write it purely from an electrostatic description. The bottom way of writing this, this particular expression is literally how, from a chemical perspective, I would write something in terms of a reaction is ultimately dictated by the forward and back reactions. And the only thing that we have to constrain in this case is that we're assuming that all these molecules stay fixed to the electrode, that none of them are popping off and none are coming back on. If you have that in mind, then the fraction of molecules that are in the oxidizer A form as a function of potential should be related to the forward and back rate constants in this particular way. This first order differential equation, that should define this type of electrochemical experiment. Okay, it turns out that very smart and famous people that preceded me by several years actually before I was born were thinking about the same experiment and the same formulation and could have given you the same slide. And the only thing is they only solved this case when we were working with reactions where the forward and back reactions were so fast that the system was essentially under equilibrium in all cases. For that case, which Laveron described in the late 70s, it turns out that an equation for the fraction of molecules at any point in time, at any potential, that were in the oxidized form is given by this really simple expression, which is essentially the Fermi function. And if you plotted the fraction of molecules in this oxidized form as a function of potential, all the molecules would start out oxidized until at some point they all transition and become reduced. And the derivative of this sort of plot gives you the voltammogram that may be familiar to those of you who've done experiments like this on a metal electrode. You get two Gaussian type looking functions that are normally stacked right on top of each other. Okay, this situation had been worked out, like I said, for 4+ decades. Okay. The other cases where that's not true, when those rate constants are not super fast, when you're not at equilibrium, it turns out had never been solved before. Okay, so the answer for any other experiment where those rate constants were not super fast had escaped people. And this is one of the second ways that we've contributed to this area. And I apologize up front because, again, the point of this talk is not to give math-based insight. But the solution that you see here in the middle, in the very tiny font, which probably hurts your eyes if you look at it, is an expression that is the fraction of molecules at any potential when Kf and Kb are written for semiconductors like I did several slides back. This expression is horrifically ugly, and yet it is an exact and precise way of describing how these types of systems behave. And again, specifically, if you know what these gamma values are, I can take this expression and make a spreadsheet and effectively predict what the voltammogram would look like in this particular case. Okay, that's what I'm going to do here. I'm going to spare you the math, and I'm just going to cut to the chase in terms of the answer. So here we're going to look at the first case where we have a semiconductor electrode in contact with the solution, and we have molecules stuck on the interface. And we're going to assume the simple ideal case where all the potential is dropping in the semiconductor. Again, this in practice never truly happens, but this is the simplest case to think about. What you see here in a hypnotic sort of fashion is a plot of the current versus potential, and this is normalized in a way so we can have this all on the same scale. Where each of these voltammograms, each color that you're seeing here, is a voltammogram that would correspond to this ideal experiment, where the only thing that's changing is the scan rate, or more specifically, the time scale of the experiment. If we normalize the experiment in terms of the rate constant for charge transfer divided by the scan rate, that's what this M value here is. And so as we have a large M value, this black data kind of looks familiar. As that M value gets smaller and smaller, we see that the voltammetry gets this asymmetric shape. As you do an experiment faster than your chemistry can keep up on a semiconductor electrode, you should start to see asymmetry appear. That's what all of that math tells us in terms of how this should work. If we look at a related system, but now we add a little bit more realistic description, where some of the potential is dropping in the semiconductor where we would want it, but now some of it is dropping at the interface. We're losing some of the potential specifically in the interface. And in this case, we're going to keep the time scale of the experiment fixed. And all we're doing is we're changing the amount of potential that's dropping at the interface. We can see that the more potential that we drop across the interface, the more distortion we should get in our data. We should lose that asymmetry, and eventually at some point, our data is going to start to kind of look like a metal electrode. That specifically means that this anodic peak is growing in. It's not because the chemistry in itself has changed. There's nothing about the molecules that we're assuming is changing. It's just how the potential is being distributed because of how you're doing the experiment. If you do the same experiment, but now instead of the potential dropping across the interface, but it's dropping across the semiconductor and in the solution, you keep the time scale constant. Again, you're going to see a distortion in your data, but you see a different type of distortion. You don't see this asymmetry really going away, but you do see a loss in terms of intensity of your reduction peak, which tells you that now you can no longer trust sort of simple relations in terms of scan rate and peak current density, because there's a complex interaction when you lose potential out here. Okay, all this to say, these basic insights are, if you believe me that the shapes of the data have information, and if you believe me that the ugly, horrifically looking equations that I showed you previously, that I recommend you burn from your memory if you can, if you have those in hand, one in principle can take any type of experimental data, and if you feed in the physical constants into those equations, that, by the way, have no fitting constants or no fitting parameters or adjustable parameters, they only have physically measurable or knowable parameters of the system, then you can take experimental data like I have on the left and model it and try and analyze what does that data say. Okay, so that's what we're trying to do here. In this case, this is data on the left that has ethyl viologen stuck on N-type silicon, where we did experiments where you can clearly see experimentally for that first redox wave, you see a transition in the shape over these scan rates. Where at slow scan rates, you kind of see something that's starting to look metallic-like. At fast scan rates, you lose that anodic wave entirely. If you plug in all of the parameters that describe the molecule and the electrolyte and the silicon, you can then back out of that what the rate constant for charge transfer has to be in order to see data that looks like this. And in this case, this was our first best description. These data experimentally could be described by a model that captured this transition between the black shape to the red shape to the blue shape at these same scan rates by having a charge transfer rate constant, electron transfer rate constant with this particular value. For those of you who are kind of curious, the units look a little bit funny, but these are the units that describe charge transfer with a semiconductor electrode, at least the intrinsic rate constants. These fits also implied specifically what must be the distance between the molecule and the plane of the electrode surface in order for these data to be physically consistent with the model. Now, it turns out that rate constant is pretty much spot on what you'd expect and what you would measure by other methods. But you should be aware that if you look at the model data on the right, although there's a qualitative similarity between the experimental data, there's clearly stuff that we're not catching. Clearly, the absolute shapes aren't quite right, and the intensities of the peak currents aren't quite right. That being still the case, if we do nothing to the system but change the redox molecule from the ethyl case, the blue case, if we put a different type of redox molecule, in this case, a viologen with a phenyl group on the end, where the potential for that phenyl group is much more positive by about 100 millivolts, and we do the same measurement data, we should be able to predict with our model, if we're right, how that data changes by changing nothing else but changing the E0 for this new molecule. And so that's what the experimental data on the left show when you have a phenyl viologen on N-type silicon as you change the scan rate over the same range. The model says for that same rate constant, or that same magnitude of rate constant, that if you do that, then yes, that change of E0 will affect this type of voltammetry, where you've basically lost that oxidative wave. Because in this case, the charge transfer is slower than these experiments. And so you basically can't reoxidize the system. So qualitatively, I would say we were able to get a lot more information out of these experiments than what we had previously known to be possible. But I'm telling you, we still aren't getting the whole thing right, because clearly, again, we're not getting the peak currents exactly right. So qualitatively, we capture the shape, but not quantitatively. So here is the last little bit of detail that I think is necessary, that we were missing and that we're trying to incorporate now, at least for these types of systems. When you go back and think about having a molecule stuck on a surface, and you have an electrode surface that has charge that you're trying to pass into or out of that molecule. The capacitance for this electrode is usually written like this. In this case, the capacitance that you would measure would be the sum of the reciprocal capacitance of the system. This implies that the charge here at this surface has nothing to do with the charge of this molecule at this particular position in space. However, if you think about molecules sitting on a surface, and that the plane of where the molecules are, or the plane where electron transfer occurs, is also a plane that has charge associated or stored with it. It's possible that the charging of the electrode surface and the charging of that molecular layer are not uncoupled. If they interact with each other, if they affect each other, then the total capacitance that you would measure would be described by this yellow box. And this, incidentally, is a consequence of that paper that I alluded to before from Henry White's group. It's the same idea, except this is how it works for a semiconductor electrode. And the key point here is that this derivative here, this is how the charge is changing at this plane of electron transfer. So the redox reaction now is a function of the total capacitance of the system and vice versa. What does that mean? Okay. What that means is if you have a system where you consider the first case where the charging the electrode surface and the charging of those molecular layers, if they're totally uncoupled, if they're not related, you might predict for a certain set of conditions, you get voltammetry that looks like this. But if you consider that there's some coupling between those two layers, and this sort of stack here represents predictions where that coupling becomes stronger and stronger, the data that you should see then starts to get distorted from something that looks like this to something that looks like this, where there's now an asymmetry that gets sort of squeeze on your data. Your data gets, in this case, the peak currents, they start to shrink. Your waves get fatter. And importantly, there is this asymmetry that's starting to point in one direction versus another. That's what you should see if this coupling interaction matters. Incidentally, we started looking into this distortion of the voltammetry in a little bit more detail. And it turns out what's really useful or really cool is that this asymmetry is almost like an arrow pointing. And this asymmetry, where this is skewed, is literally pointing towards where the electrode has no charge, or what's more commonly referred to as the flat band condition of the semiconductor. The point of potential of zero charge, for those of you that maybe like the lingo of metal electrodes. Okay. If the redox transition occurs in a way that's, in this case, in the left panel, more positive than the flat band potential for the semiconductor, as denoted by this dashed line, then the asymmetry that happens with this coupling of charge points in that direction. If the redox event happens on the other side of the flat band condition, well, then you'll point in the other direction. So that asymmetry now is a guidepost, or is telling you exactly what your system is like. We got really excited about that because we wondered, because the only way this is usually measured is with impedance measurements. And I won't go off on a tangent, but I'll just tell you, I hate impedance measurements with a passion, and I'll talk your ear off afterwards if you want to know why. But the only way that's typically measured is with impedance measurements. But it turns out in simple voltammetry data, there's enough information there where you can get actually not just a qualitative, but a pretty quantitative estimate of that flat band potential too, if you know how to look. And it's not just in our data. If you go back and look at the wide literature of molecules stuck on semiconductors, and you start looking at people's data, it becomes apparent that a lot of the data that's out there has asymmetry of the type that I'm showing you. It's never talked about. In fact, it has never been talked about, principally because there was no way to understand where that asymmetry came from. But from the framework that I've been telling you, this asymmetry now comes out. And in all of these cases, I strongly believe there was coupling between the semiconductor surface and the redox molecule layer, and that was telling you where that flat band potential was in each of those cases. We've spent specifically some more time thinking about molecules on silicon, like I said. I'll focus in terms of the literature data of ferrocene stuck on silicon. I don't know why this is everyone's favorite molecule to stick on silicon, but there are literally review chapters dedicated to this idea. Again, if you look at all the data, much of that data has the same type of asymmetry that I'm talking about. And we were kind of curious, if you took a few examples from the literature from different groups, are they self-consistent with each other? Okay, long story short, here are our data from not our group, but two other groups shown below that have nothing to do with each other. These experiments had no connection between each other and were not done at the same time by the same people. In fact, they were done on different continents. The red dashed lines are the IR corrected data that we collected from their papers and we tried to clean up in order to do this analysis. The blue data is our fit to their experimentally reported data using the same data, the same parameters to describe both sets of experiments from both labs. And it turns out these two papers, as well as many of the other ones that we showed that I listed before, they all come to the consensus that the flat band, the valence band edge for silicon relative to the E0 for ferrocenium is consistently at this value. Like if you dig through all the literatures for all the people that have done silicon and ferrocene, it turns out all their data can be described in sort of a self-consistent manner. Now you can see that our blue lines don't fit their experimental data perfectly. I honestly, actually, the more we've looked at this, the more I feel it has to do with the data collection aspect. But there's still some aspects in our model that we're trying to refine in order to get a perfect fit. But we're pretty happy that on a global fit of other people's data, it seems like everything checks out. Applying that back to our data, which is stuff that we can quality control and vet, here are our now best fits of our experimentally obtained data with the ethyl and phenyl viologen. We still don't get an absolute point for point fit, but now we can capture those peak current values and we can capture the shapes much better. We can analyze these data in almost complete totality now. We're not analyzing data by looking at sort of just the peak value, but we can interpret the entire shape of the voltammogram and get physical meaning and chemical information out of that. Okay, I think I'm running out of time, so I'm going to skip most of the rest of the stuff I was going to say, and I'm going to just go to the last panel because I'm particularly interested in that. The last panel, which I'll skip this, and to say that everything that I've said for experiments where the molecule is stuck on the electrode, it also holds when you take that molecule off of the electrode, now it's diffusing in solution. So here's some of my favorite data from a guy, Carl Koval, who maybe some of you know. If you don't, you should get to know him. He's a really nice guy, but even more importantly, he's a really good scientist. And roughly in the time I was in, I think, preschool, maybe entering first grade, he collected some great voltammograms of redox active molecules with a bunch of different semiconductors. In this case, I'm showing you here in the blue plots here. These are N-type indium phosphide electrodes that are reducing and oxidizing these cobaltocinium complexes. Okay, those experiments, super easy to collect, have not been analyzed in any detail because, again, there has been a way to analyze it. You take the framework that I presented to you, you change the math a little bit. I won't bore you with the details. It turns out that everything is still self-consistent. So our models of his experimental data are shown here on these right plots, where we can capture the qualitative features of these otherwise very funny looking voltammograms at different scan rates. And hopefully we can report that soon. Okay, I'll just summarize and say that we think there is a way now to understand the meaning of the voltammograms with semiconductors collected in the dark. And everything I've told you is, I think, the best way to do that. There's still some more parts that are missing. There's some finer details that I think we can improve upon, but there's a framework there. And everything that I've shown you, I should say, was collected not by me, but by these talented people. So I thank them for their hard work and their efforts. And I guess with that, I will end the talk and maybe go back to Gary if he's still online. So thank you.
He's still here. It says we heart specs.
It does, Gary. You know, I will say I've given several different talks with these autostereograms, and actually several people have complained to me to say they see nothing and they think that I was wasting their time. You're the first person to see it and see it instantly. So your eyes are as sharp as ever.
I think that's incredibly sad. I can do it, to tell you the truth. Can I ask a question, Aaron, since I've got my microphone on? It's really good, Stephen. And even though we did hear at the photochemistry meeting, I will look forward to hearing it the third and the fourth time, because each time I get a little bit more information sink in, and it's incredibly valuable. When you did that first assessment of your model relative to data, where you have the methyl viologen attached to the surface, and I'm sorry, but Mike was struggling with D, but I'm going to go back to D. You had a distance there of 4.8 angstroms. I've forgotten what that is a measure of. And if I think of it as the distance between the semiconductor surface and the methyl viologen, it seems wrong. So D is a layer on the electrode surface, isn't it? That's missed. Yeah, that's that one. Yeah.
Yeah.
So what is 4.8?
So this is as we are both modeling and interpreting, and we're trying to get molecular dynamics to get some firmer confirmation. But this tether, which it's not immediately obvious to show, it's actually pretty floppy. Okay, so you have a linear alkyl chain. That entire tether length is much longer than that distance. There's no through bond tunneling in terms of this case. What happens is the molecule bends over. And we think on average, then that's the average distance for charge transfer.
Okay. That means that my question wasn't quite as naive as first sounded. Okay, so that is the average distance between the electrode surface and the methyl biologen.
Yep.
Okay, that's still quite a distance, isn't it?
It's still, yeah, that's right.
It would, yeah. Okay. I might have another question, but I'll shut up for this moment. But thank you again for that.
I've got a question, Aaron.
Go for
Hi,
it.
Neil.
Okay, Steve, this is great stuff. And I knew all of the old guys that you cited there, so I'm probably the only one in this group that did, including Gersher. But one of the things I am curious about, how do you handle the energetic heterogeneity of these surfaces? So you're making the assumption that all of these molecules are attached in exactly the same configuration, that there are no energetic barriers that are present on nanometer length scales, or does that really matter at this point? What if some of these molecules are perfectly well attached, but they're sitting on a blocked site, maybe that's just not doped properly, or something of that sort?
So you're right. That is the assumption we make for all of these. These are macro electrodes. We have wondered a lot about that. But in terms of our assumption, it doesn't seem that the level of detail that you're talking about ultimately will explain, or including that explains our experimental data. I guess we take the Occam's razor, the simplest viewpoint.
Yeah.
However, I have been very interested in whether that explicitly matters or not. And so we've been trying to tackle that experimentally, but we hit a roadblock. Experimentally, the way we tried to do that is make our contact area much smaller so that we can maybe start to identify when they're, so we try to make these micro or nano electrodes.
Right.
What I didn't know about, or what didn't occur to me, is that those micro and nano electrodes, they become hideously sensitive to IR distortion in the radial dimension. And so you get a different type of distortion of the shape, which we're still trying to work out, but it makes the analysis even harder.
Yeah.
So
I'll bet.
so we don't have, I would say, the smoking gun type experimental data yet to address what you're asking, but I have the same question.
So I'll go look for the paper, but there's a kind of a brilliant paper that slipped beneath the radar that Akira Fujishima published on boron doped diamond years ago, where he varied the doping level in that system and was able to see pretty pronounced changes in electron transfer rates just due to the heterogeneity of the distribution of the dopant. And I don't know whether anybody really picked up on that beyond that point, but I'll go looking for it. It might give you some clues. Otherwise, this is fantastic stuff.
Thanks, Neil. I appreciate it.
All right, I'm gonna let Obadiah ask a question, and then we probably need to sign off. Those of you, if you've got other commitments, thank you for your time. We appreciate it.
Yeah, thanks, Stephen. This was really, really cool. I guess first, a little follow up on what you were just saying about the micro electrodes. I don't know if it's the same problem, but that sounds awfully similar to problems that I tackled years ago trying to understand distortions in current density with an AFM tip, where you have this essentially a nano electrode and it modifies the geometry of essentially the diffusion, which really changes the current densities you can get. So there might be things that could be learned from that literature if that's the problem that you're describing. The other thing was just a simple clarifying question on this slide. Is that centimeter to the fourth per second just because it's bimolecular on a surface?
Yeah, that's right. It's bimolecular because now you have the supply of electrons and the molecule. So it's that aspect that contributes then to the weird units of centimeters of fourth per second.
Yeah, the way I think about it is that, you know, in his band bending pictures, right, it captures that kind of volumetric aspect of the near surface region of the electrode that is providing the holes or the electrons to drive the redox reaction. So that's a cubic centimeter parameter. And then you've got the centimeter per second rate constant.
Okay, so that's not quite what I was thinking. I was imagining it as being directly analogous to a bulk bimolecular rate constant, where you wind up with centimeter cubed per second instead of centimeter to the fourth per second. But okay, it's a little different.
Well, it's that, but this is ultimately a current density in terms of what this relates to. So I think it is what you're saying, Obadiah, but it's just the units for a heterogeneous reaction are a little bit different than a homogeneous reaction.
Okay.
I will just say one thing in terms of the distortion. You might be right. I'm going to have to take a look at that because I'm not as familiar with IR distortion in the AFM type experiments. But I will say that Christian Amator had a really nice set of papers that describe for really small contacts. The issue is that in the radial direction, the current distribution is a function of the radius position. You basically have an IR distortion that now depends on R, and on these small electrodes, for reasons that are not so obvious but ends up being true, that dependence becomes fairly severe under a lot of experimental conditions, where especially at faster scan rates. So you get this radial distribution of the current and effectively different potentials that you're at as a function of the position in the radial direction on your electrode, and that distorts or smears out your voltammetry in addition to everything I talked about. And
I think that's very closely related to what I was saying, which is essentially that when you have when you have an electrode that's big enough that it can be approximated as a plane, the current can essentially be modeled as like a one-dimensional function, because the potential doesn't change in that sort of radial coordinate.
Yeah.
Whereas when you have a really sharp electrode, suddenly it does change, and essentially you get a higher dimensionality of a diffusion, and also a potential gradient across the surface of your electrode that you wouldn't have otherwise.
yeah, that's it. That's exactly right. And decoupling that, at least to me, seems to be much more difficult, and it's less clean, I would say. So we haven't been able to get. We can get data, but we haven't been able to, let's say, correct it in a way that's satisfying yet.
Right. Yeah, I'm not saying it's easy. I'm I was just intrigued that it's a parallel problem from different places.
Yep.
We've been talking about that work as well, Obadiah, in my group, with the scanning electrochemical cell microscopy, and how do you capture the fact that you've got this kind of cone-like shape away from the surface that you could be gathering current from. And then the complexity, of course, in the organics is that we've got potentially a 2D or a 3D system instead of a 1D construct, like what we've seen from Stephen with the semiconductor, the Helmholtz layer, and the diffuse layer. Now we've got all sorts of extra stuff going on as well. So,
Great.
Okay. I think with that, in the interest of everybody's time, Stephen, thank you again. This was a fantastic tutorial. I saw from the traffic in the chats, I was getting lots of thoughts, inspiration. So again, thank you very much. We really appreciate it. And I have a feeling you may be getting some questions from some students if you're open to it via email.
Yeah, sure. Please send them. I will answer any and all questions.
Okay. All right, great. Thank you, everybody. And we'll see you again in 2 weeks, and we will hear Obadiah's perspective on charge transfer. All right. Bye.